Welcome to this explainer. Today, we are diving into the absolute bedrock of computer science. We're talking about the array. Whether you're running a basic calculator app or firing up a massive AI model, the way data gets structured in the background literally dictates how efficiently that software runs. So just think about this for a second. How on earth does a computer keep millions or even billions of data points organized and instantly accessible? Without a really rigid, highly predictable filing system, trying to find a single piece of information in memory would be exactly like searching a massive, pitch-black warehouse without a flashlight. Here is our roadmap for today. First, we'll meet the array. Then, we'll look at finding data in memory, adding dimensions, unique array types, and finally, array operations. Okay, let's jump right in. Part 1, meet the array. Now, looking at the technical definition, an array is a linear data structure. But the absolutely crucial takeaway from the source material is that it's a collection of the exact same data type, so like all integers, and they are stored in contiguous memory. There is no mixing data types here and absolutely no scattered storage. These items are sitting shoulder to shoulder. And here's where it gets interesting. Because while we humans generally picture an array horizontally, just as a simple numbered list, the physical reality inside your machine is actually quite different. The system is allocating a literal, consecutive block of physical RAM vertically down the line to store these values. Because of this contiguous storage and zero-based indexing, we get a real superpower. It's called random access. This means it takes the exact same amount of computing time, which we call O1, to access the very first element as it does the millionth. The computer doesn't have to scan through the whole list. It basically just teleports directly to your data. Moving right along to Section 2, finding data in memory. Now, don't let this formula intimidate you. The system just uses this straightforward math to calculate exactly where your data physically lives in the RAM. It's really no different than figuring out a specific mailbox number based on the street address of an apartment building. Let's break these variables down really quickly. B is just our base address, meaning where the very first element lives. W is the byte weight or size of each item, say 4 bytes if it's an integer. Then the index is our target position, and the lower bound is our starting point, which is usually just 0. Let's apply this to a concrete example from our sources to see how simple it actually is. Say we want to find the 5th element, which sits at index 4. If we start at a base address of 1000, we simply multiply that 4-byte size by our index of 4. That gives us 16. Add that 16 to our base, and boom, we land instantly at memory address 1016. That little bit of math right there, that is the secret behind that lightning-fast O of 1 speed. All right, Section 3, adding dimensions. So once we've evolved past a basic one-dimensional row, we can actually add a second dimension to create a matrix. Suddenly, we've moved from a simple list to something more like a spreadsheet or a chessboard. Now we are locating data using 2 indexes, one for the row and one for the column. But here is a fascinating physical constraint. RAM is strictly linear. It doesn't actually have 2D grids, so the hardware literally has to flatten that 2D matrix back into a single contiguous line. It does this either by stacking it row by row or column by column. And honestly, knowing exactly how your specific system flattens this data is an absolute game changer for writing highly optimized code. And of course, we aren't just limited to 2 dimensions. A 3D array is exactly how your computer processes a digital image. It uses height, width, and a 3rd dimension just for the red, green, and blue color channels. It's literally how we map complex real-world visual reality into traversable math. Next up, Section 4, unique array types. When you are dealing with varied data, you might use something called a jagged array. This is essentially an array of subarrays of totally different sizes, which is absolutely perfect for hierarchical data. But on the flip side, if you really want to optimize CPU caching, you'd use parallel arrays. Think about it. Instead of grouping all of an employee's data together, we put all the employee IDs in one 1D array and all their salaries in another. It completely separates the attributes, but it dramatically speeds up processing when you only need to run calculations on one specific metric. And finally, Section 5, array operations. When it comes to actually manipulating this data, the trade-offs become pretty clear. Accessing or appending data at the end, that is a lightning-fast O of 1 operation. But if you try inserting an item at the very beginning, well, that forces the computer to physically shift every single subsequent element down one slot in memory. That is a much slower ON operation.
Similarly, trying to find data requires ON for a standard linear search, but that time drops beautifully to O log n with a binary search, as long as the array is sorted. Now, understanding this memory structure isn't just some academic exercise. N-dimensional arrays, also known as tensors, are the absolute bedrock of modern machine learning. Frameworks like TensorFlow and PyTorch, they are built almost entirely just to manipulate these massive arrays efficiently. Every single time an AI recognizes a face or generates a block of text, it is just crunching math through multi-dimensional arrays. So I want to leave you with this to consider. We've really just been looking at the lowest possible level of how data sits in RAM. Just imagine how these incredibly basic, contiguous blocks of memory are scaling up right this second, linking together by the billions to build the neural networks of tomorrow. It literally all starts with a simple array. Thanks for joining me for this explainer, and definitely keep exploring the foundations of our digital world.